Okay, the next type of transformation is dilation. And a dilation is a transformation that may change the size of a figure. Okay, and the scale factor is always going to be the image length over the pre-image length. Remember, the image is the finished product, or the one with the prime. Pre-image is the one without the prime. Okay, we're going to look at example 1. Is this dilation an enlargement, reduction, or congruence transformation? What is the scale factor? All right, well, we know it's not a congruence because it's a different size. Okay, the new one we are told is the one with the primes. So since the one with the primes is bigger, this is going to be an enlargement. So I'm going to line that. Okay, now what we need to do is we need to do the image length over the pre-image length. Again, the image is a new one, so that's this one here. All we have to do here is count the blocks. We've got 1, 2, 3, 4, 5, 6. So our scale factor is 6 over, count these blocks, 1, 2, 3, 6 over 3. So our scale factor is 2, and it is an enlargement. And example 2. What are the coordinates of A, B, C centered at the origin? Okay, given a scale factor of 2. Okay, so what we're going to do is we're going to take this triangle ABC, and it's centered at the origin. So given a scale factor of 2, that means the new triangle is going to go twice as far in this direction, twice as far to B, and twice as far to C. So we're just going to multiply each of these by 2. So A prime is going to be 14 and 20. B prime is 8 and negative 12. And C prime, let's put it up here. C prime is going to be negative 4, 6. And that's given a scale factor of 2. So the answer to A is up here. The answer to B down here is a scale factor of 1/3. So these are all going to be 1/3 as far as these. So we're just going to divide all these by 3. So this one, A prime, is going to be 7 over 3 and 10 over 3. B prime is 4 over 3, and negative 6 over 3 was just negative 2. And then C prime in this case is going to be negative 2 over 3 and 1. And that's A and B. Again, so scale factor 2, you're just going to double all these, since it's centered at the origin. Twice as far in that direction, twice as far in that direction, twice as far in that direction. Scale factor of 1/3, we're going 1/3 of the way, so 7 divided by 3, etc. Okay? Example 3. Draw the image of each figure under a dilation centered at the origin with the given scale factor. Okay, so our scale factor here is 1/2, so we're going to make this one half as big. Okay. All we need to do is center it at the origin, so we know we're going out, we're going up 3 and up 3 this way. Okay, so halfway would be 1/2 and 1/2. We're going over this way, 1, 2, 3, 4, 5, so we're going to go over 1, 2.5. And back 2.5. Okay, then we're going to try to draw a straight line here. And yours should come through the middle of those blocks. Like so. Okay. Now, and that would be our scale factor of 1/2. Again, the new figure is smaller than the old figure, so it's a fraction like that. Okay, this one 2 over 1, so this one's getting bigger. Okay, so if we went out 2, now we're going to go out twice that, which would be 4. We're going up 2, so we're going to go on up 4, back 2, and back 4, down 2, and down. Okay, now we're just going to try and draw a circle here. Okay, and that is our dilation, which is an enlargement, scale factor of 2. Alright, let's move on to tessellations. You've seen these before, although you might not know what they're called. And reflections, translations, and rotations, which we've just used, can be used to create tessellations. Using polygons. A tessellation is a pattern that covers a plane by transforming the same figure or set of figures so that there are no overlaps or empty spaces. It has to completely cover it, like the tile on the floor is an example of a tessellation. Okay. This right here is an example of a tessellation, and these are all hexagons, so they're tessellating right there. The sum of the measures of the angle surrounding any point and a vertex, for instance right here, draw a circle around it, you know they all have to add up to 360 degrees. Okay? Now, for these, we need regular polygons. So a regular polygon has an interior angle with a measure that is a factor of 360, then the polygon will tessellate the plane. In other words, that will cover the plane with no gaps or overlaps. Okay? Alright, so let's look at some of these. Here's some examples of tessellations. This is a little fancy one right here. And another one is right here. Now these aren't all the same figure. This is looks like a hexagon in the middle, and then let's add some other ones. Okay, so sometimes you have to add other pictures, other shapes. This one is another example, and you can see if you can find out where that image is from. There. This one's probably cut out of the textbook, I think. Okay, so example 1, we're going to determine whether the following polygons will tessellate. Explain your answer. Okay, so we said up here the regular polygon has an interior angle with a measure that is a factor of 360. So we need to find interior angles of all of these. Okay, we could use the sum of the interior angles, or we can find the exterior angle and subtract it from 180, and that would give us the interior angle. So we know that all exterior is going to be 360. In this case, it's a triangle, so 360 divided by 3 equals 120. That equals the exterior angle. And if we subtract that from 180, it gives us 60 for the interior angle. And if that's a factor of 360, which it is, this will tessellate the plane. Yes. In this case, explaining your answer will be showing this work. Let's look at a regular pentagon. First we'll find the exterior angle. So our exterior angle equals 360 divided by 5, which equals 72. That's our exterior. Our interior angle is going to be 180 minus 72, which equals 108. And if we try to divide that into 360, that's not going to work. So since this is not a factor of 360, this does not tessellate the plane. Let's do 360. Let's do 108 into 360, and that'll be 3 times, so that's 324, and that gives us, what's that, 360 left over, so it's going to be repeating that, right? So that doesn't work. Alright, let's look at the square. Square, alright, we've got 360 divided by 4, so So that equals 90 for our exterior angle, 180 minus 90 equals 90 for our interior angle. Okay, so our interior angle equals 90. That does go into 360 evenly, so our answer on that one is yes. And then regular 24 gone. So let's do 360 divided by 24. That equals 15. Okay. So our exterior angle is 15. Our interior angle is going to be 180 minus 15, which is 165. And that is not a factor of 360, so our answer for that one is going to be, oh, that's example 1. Let's look at the next example. Now we've got some practice here. Alright, let's determine whether the following transformations are translation, reflection, rotation, or dilation. If it's dilation, state whether it is a reduction or an enlargement. The first one, we've got this figure right here, and we're just moving it across. We haven't turned it or anything, and we're just sliding it. So sliding, we know that's a translation. So we're just going to get translation right here. Okay, this one right here, we're going from here to this one. It's getting bigger, so that's going to be an enlargement. You don't have to write that it's a dilation and an enlargement, because we know if it's an enlargement, it was a dilation. This one, shrinking. Okay, so that one's going to be a reduction. This one right here, looks like we rotated that one, so we've got a rotation there. That looks like it's 90 degrees. Okay, and then this one here, just flip that over there, so we're going to call that a reflection. Number 6. Determine whether the shapes will have point, reflectional, rotational symmetry. If they have reflectional symmetry, sketch the lines over the shape. The rotational, state the angle of rotation. Okay, so reflectional, yes, because it'll go through here. Nope, not through there. Let's try that again. Remember that. Pen back here. Okay, we're going to go this way, straight down through there. That's 1, 2, 3, 4, and 5. Your line should look better than that. So it does have rotational symmetry. And it rotates as well, so this will go around this way, 2, 3, 4, 5, so 360 divided by 5 equals 72. So that has reflectional and rotational. It does not have point because we can't go halfway around the circle and have that match. This one here, number 7, we can draw a line right here. So it has reflectional. Rotational, we have to go all the way around the circle to match up, so it doesn't have rotational. And point would be halfway around and match up, and that doesn't work, so that just has reflectional. Number 8. This one, well, let's see, it doesn't have, it has reflectional right there, so that's reflectional. And it doesn't have rotational because you have to go all the way around, so that's just reflectional right there. This one here, reflectional because we can go through here, we can go through here, we can go through here, and go through here, and have it flip over onto itself, so that's reflectional. Rotational, 1, 2, 3, 4, so 360. Divided by 4 equals 90 degrees for rotational. And that is the end of this lesson.